velocity at which it passes where?
Not.
Well, actually, it comes in there with, well, we could figure that out, but I think it comes in with a 0 velocity initially. Because what it's doing, here's your impeller turning, and there's a tube here with the liquid in it, and the liquid's coming in and then being thrown out radially. So it's coming in here, and as it turns and then starts to move outward radially because of the impeller fins, that right when it first enters there, it's got 0 velocity.
So if it has 0 velocity when it comes in, and its radial acceleration is 0, how does it move away from the origin?
Well, that's a good question. And so that's one that I want to ponder. So let's do the theta calculation first on the acceleration and see what that gives us, and then we'll come back to that. Okay. I think you might be onto something there. Okay. So this guy we know is, now think about these terms, trying to get these into your head. This is the theta directed term. So thinking of, oftentimes I fall back to thinking of circular motion because I have a good sense of that. So in circular motion, I know that I could be speeding up in circular motion, couldn't I? And so it could have a tangential kind of term like an R alpha. And that's exactly what's showing up there, R theta double dot as a possibility. And then you have to add that potential, that weird thing, the Coriolis type of term, to R dot theta dot. Now we've discovered earlier that theta double dot was 0, so this term's out of there. We have an R dot expression and we have a kappa for theta dot. So we just drop those in there. And so what we're finding then is that the theta directed term apparently is our total magnitude of our acceleration, and that's going to be equal to then just this Coriolis term, just the Coriolis term. And so we're going to put our R dot term in here times 2, and we're going to tag another kappa on for theta dot. So we're going to get a 2 R naught kappa squared sinh of kappa t. Here's the R naught. I want to go back to your comment, see if I had that, if my thoughts there were correct. This thing's telling us that the only acceleration that exists as it moves out through here radially, is in the theta direction. Okay. If we look back at the velocity vector, that's made up of an R dot R hat plus an R theta dot theta hat. There is an R dot, isn't there? And R dot was that first derivative which we have down here. And at time 0, what was that sinh graph which I erased? What's the sinh of 0? No, sinh of 0 is 0. So R dot is 0 at time 0, right? Okay, so R dot is indeed 0 at time 0. And then R dot's going to grow. Let me draw that. R dot, yeah, it grows. Here's your type of sinh function. Whoops. Yeah, there is. Okay. So I'll tell you what I want to do. I just want to make sure I didn't make a mistake and that you folks just went along with me on it.
I've got the same thing, actually.
Okay. So what I want to do is I want to look at what I kind of penciled in here to see if, no, I must have made a mistake somewhere because I'm looking at my work here. Check this out. Where did I make a mistake on the board? So here's our theta double dot term. Here's our, we're good on the r dot. We're good on the r double dot. Here's the radial one, which I said zeroed out. Ah, look at that.
There's a square term there.
Boy.
Oh yeah, you have to square the code. Okay.
You, how do you get two squares? You got it?
How did I get a square on that?
Yeah, why? Because I don't see
R double dot, it's just constant on the outside. There's no need to do any part of your strings.
Here's the r dot. Oh, r double
You wrote a
dot.
square on
R
it.
double dot. How did I get a square on my cosh and my notes there?
Impressive.
I think you wrote it in because you have R double dot up there on your writing without a square, no, up on your paper
Yes.
with no square term, but you just wrote it in when you did the R,
Oh.
the radial acceleration.
Okay,
You wrote in
so-
the square and there's
Okay,
no
so I think my notes are wrong that I have penciled up there. I think the stuff we did here on the board is correct.
Which is interesting. It still says there's no radial acceleration.
Right, still says that. Well, you know what I'm going to do? I have a solution key to these things that you folks don't have access to. I'll go check that, and I'll let you know in the next class session. Okay? Okay. But anyway, if nothing else, it's a good review for you of a little bit on the hyperbolics, which is a useful thing. And then I'll confirm this and get back to you at the next class session. Okay. Let's do another one and see if we can get it right.
Well, for all we know, we did get it right. Your notes are wrong.
Yeah, I believe we got it right. Okay. I think it would be useful to back up and do another normal tangential problem. And we've got a little less than a half an hour left. Let's take a look at one like this. Where we have a car running a test between pylons that are equally spaced, and we want the vehicle to pass in a sinusoidal type of curve, maintaining that nice smooth sinusoidal type of curve. And we don't want the acceleration, the lateral acceleration, the sideways acceleration to exceed 7/10 of a g. 7/10 of a g. Probably so that the tires wouldn't break loose. Given the type of rubber, the inflation of the tires, the tread, and the pavement condition. That combination is what gives you the break loose criteria. So you don't want to exceed a certain acceleration given the combination of the tire characteristics and the pavement in which it's contacting.
The weight of the car, too.
Well, the weight of the car establishes the footprint of the tire then, yeah. So it gets more complex than just treating it as a particle, which is what we're doing here. We're treating the whole vehicle as a particle. So we want the lateral acceleration not to exceed 7/10 of a g. Testers want to design a slalom through which the maximum speed is 80 kilometers per hour. What cone spacing should be used? What cone spacing should be used? Okay, so let me see if I can either rotate the boards. We'll try that. And
Is this log going Is this car going at constant speed? Good question.
Let's assume that it is. Okay, so we're going to assume the car is moving through that sinusoidal path at a constant speed. And we don't want it to exceed that 7/10 of a g lateral acceleration. Testers wish to design the slalom through that, so we're looking, and we want the, we want a maximum, well, I'm not sure if we're going to make that assumption, through which the maximum speed is 80 kilometers per hour. Okay. All right, maximum speed is 80 kilometers per hour. So the way they've drawn this, if I use that left pylon as my reference, then it looks like my path is going to look like this. We don't want to deviate from the line of cones by more than 3 meters to either side. So it looks like we have a cosine model here. If I establish x and y axes. So we'll do a little math review here. It looks like we have that y is described as an amplitude of 3 on the cosine function. And it looks like the spacing, we call this L between the pylons, distance L. So it looks like the period of this function is 2L. So the period is equal to 2L, and we know that a sinusoid's period is given as 2 pi over omega. So it looks like our omega is pi over L. For our model. And the model we're coming up with is a cosine model with an omega x of this style. So it looks like our equation that describes the curve is 3 cosine of pi x over L. Right there.
Would we rather have this as a function of time?
Excuse me?
Would we rather have this as a function of time? As if we...
Okay, well right now we've got it as a function of position, clearly. Okay? And we want the speed to be no greater than 80 kilometers per hour. Now, since we've given the lateral dimensions of meters, let's first of all make sure that we get the kilometers per hour kicked over into meters per second. Okay? What I want to do is try playing with the mathematics of this y as a function of x before I start trying to figure out some function of time as it's moving along the path, and see if I can get at the necessary answer without having to come up with that thinking on time. Okay? So a maximum speed, V max, is 80 kilometers per hour. And I want to get this in terms of meters per second. So I'm looking for this in meters per second. So all I do, whenever I'm trying to convert units, I always write them down. Because it's, and I don't know if you've made this mistake like I do occasionally, even after all these years, is I sometimes get those conversion factors upside down. So it's a safe bet to say, I mean, you know how long these problems get sometimes. And what you don't want to do is make some mistake back up here that then is going to carry through a whole page or two of work. So what I do is I write down what I'm looking for, and then here's what I'm starting with, the given information. And I know I have 1,000 meters in 1 kilometer. And I know there's 3,600 seconds in an hour. And so there we can kick that into meters per second. So if I knock that on down, then I'm going to get 80,000 over 3,600. Or I can knock off 100 here. If I knock off 100, I could then reduce this. If I want to write an exact value down for this, I can reduce this down, and I can see this as 80 times 10 over, oh, what would factor nicely there? 9 times 4. And knock the 4 out of the 80. Actually, 4 out of 80 is 20 times the 10. Leave the 10 in there. And so we end up with 200/9 meters per second. And with your calculator, you can punch that real quickly. I oftentimes like to carry them along in their exact form, though. Okay. 22.2 repeating meters per second. Okay, that's the maximum speed. Okay. Now, when you're at this point on this path, you're at an inflection point on the cosine function. Normal acceleration? 0. Everybody comfortable with that? Normal acceleration is going to be 0. AN equals 0, right there. Okay, so we know that. When it reaches the crest or trough of the cosine function, in other words, it's directly sideways to the pylon, it's going to have its tightest curvature, isn't it? Tightest curvature. And so it's going to have its normal acceleration right there. Normal acceleration right there. And we know that normal acceleration is v squared over rho. V squared over rho. We also know that this rho is at its smallest value, right? Rho minimum at the crest trough position, which is going to give you the greatest normal acceleration reading. The greatest normal acceleration reading.
If our velocity is constant.
Well, let's say it is. No. We could be hitting the accelerator as we're moving through this thing, or slamming the brakes on, and we could give it a tangential component. But we have no way of knowing. All they're saying is don't go faster than 80 kilometers per hour. So I think what you're saying is correct. We could get a situation where we could exceed that 7/10 of a g. And I should write that somewhere here in this problem. The A max, we don't want it to exceed 7/10 of a g. That's a criteria in the problem. So I think what I want to do is ignore the fact that I might be able to hit the accelerator, slam on the brakes, and give it a pretty hefty tangential acceleration. I kind of want to ignore that. I kind of want to investigate this tightest point of curvature and see if we can go ahead and pin this down at that location. Okay? And see if we come up with what they're looking for, because they did provide us an answer to what their thinking was on this. You with me? Okay. So let's see. I guess we could drop in our 22.2 here, right, for our speed, maximum allowable speed, as we're going through the tightest part of this curve. Okay, so let's use it, and let's go in here and put in that 22.2 repeating, squared, divided by this radius of curvature. And I don't want this to exceed 0.7 g. Okay? And so I want that acceleration reading to be less than or equal to 0.7 g. So if we look at this now, the only thing that's sitting here is this rho. Radius of curvature. How do we figure out radius of curvature?
You can solve for it.
Solve for it. How do we do that? That's the trouble when you respond to a question, I ask you another one.
Well, we have the
As
inequality
it is,
set
you
up
could
there.
find the maximum.
We have
So
what?
we could get a range of values that rho could be, but not necessarily pin it down to one
Just
of
based
them.
on what you have up there, the substitute multiply both sides by rho divided by 0.7 g.
Okay, so we could get the radius of curvature, couldn't we?
That would be the maximum.
Okay, so we could get the radius of curvature. Let's go ahead and do that. And so if I kick it up over here, assuming everything's positive, which it is, then we're going to end up with a rho value that must be greater than or equal to this 22.2 squared over 0.7 g. Our units in this problem were the metric system, and so we want to use 9.81 right there. And so we have 22.2 squared, repeating, over our 0.7 times 9.81. If somebody would punch that up for me.
71.77 meters.
71.77.
Yes.
77 units on this are going to be meters. So we want a radius of curvature that is going to be greater than or equal to that value. Well, that's all looking well and good, but that isn't what the question asked. The question asked, what's the distance to go out there on the test track and set these pylons at?
So we define this curvature as a function of L. L is a function of radius.
Okay, so how are we going to find the radius of curvature? Here's our path. Here's our path. How are we going to find the radius of curvature? Well, we go pull out our math book, right? Because most people don't memorize the formula for radius of curvature. If you look in the back of your textbook, I believe it's there. And I'm going to erase our Vmax calculation over here so I have enough room to do this. And what I do remember is that we need derivatives. We need the second derivative of this, and we also need, well, obviously the first derivative. And those show up when we formulate that. So if I do the first derivative of this, y prime is negative 3 pi over L sine of pi x over L. And then if I get the y double prime, we have to crank it again, and we get minus 3 pi squared over L squared cosine of pi x over L. Right? And then, let me see how good my memory is. Am I good so far? Squared to the 3 halves. I don't know. Is that right?
You've got it inverted. You're finding K right now, I believe.
Oh, the curvature.
And then rho
Okay.
would be 1 over K.
Good. This is 1 over the curvature,
Yes,
Yeah.
you got it.
or 1 over the radius. Is that it?
You got it.
Okay, good.
That y prime squared. That's the one.
Yeah, that's I'm sorry for my handwriting there. That's a y prime being squared inside there. Yep. Now, before we drop all these derivatives in there, we're at this location, are we not? And we define this as this nicely defined cosine function coming off this location over here. So it looks like we're at location at L.
Yeah.
So that might make things a little nicer for us. So looking at that, we have y prime at x equals L is going to be the sine of pi in there, isn't it?
Yeah, 0.
Okay, so that's going to turn out to be 0. Minus 3 pi over L sine of pi L over L. That zeroes out. Our y double prime, let's hope that doesn't go to 0. If that goes to 0, we're in trouble.
I think it goes to -3.
Thank you. Okay. So we end up with a negative 3 pi squared over L squared with a cosine pi L over L, which is the cosine at pi. Negative 1 is that value. So that turns this positive, which is very nice. So we have 3 pi squared over L squared. And that denominator on this curvature equation, curvature formula, that denominator, this just turns to 1, doesn't it? So we end up with 1 over the radius of curvature is simply that second derivative. So 1 over the radius of curvature is equal to this y double prime, which means our radius of curvature is going to be the reciprocal of this, which is going to be L squared over 3 pi squared. And we said that this value on this other board, that value must be greater than or equal to this 71.77 meters. So let's see what we get. We get L then is going to have to be, we're going to go for the smallest value here, making it equal to this. So equal to this, so this is going to be approximate now, and it's going to be the square root of the 3 pi squared 71.77 term, and that gives us what?
46.09.
Does that work?
Yeah.
It's because the answer is 46.1.
46.1 meters. Okay, good. Okay, so the discussion we had a little while ago about hitting the accelerator, jamming on the brakes, where we could create a tangential acceleration. If we jammed on the brakes, we'd give it a big negative acceleration like that. Or if we hit the accelerator, give it a big jump in that direction, we could exceed that 0.7 of a g. So I think the assumption would be to just go that no, we're going to be a nice, smooth, skilled driver, and during the tightest part of the curve, we're going to make sure we don't exceed that 0.7 of a g normal acceleration. Okay.
Actually, if you had any tangential acceleration at that point,
Yeah, if you were up at, if you were at that speed.
well, we're only considering the maximum acceleration as normal, so again, it doesn't really make a difference on that part.
Correct. It doesn't make a difference. Okay, so I think that'll do it for today, and hopefully we were able to review a little bit of trigonometry today, a little bit of hyperbolic function stuff, and then also hopefully solidified your understanding a little bit about these components. Okay, we'll see you on next week.